Hi, welcome everyone to George Mason University Observatory. It's now 8 p.m. Eastern. We're going to have some introductory slides while we wait for everyone to get connected. The good news tonight is that we have the weather is cooperating at the moment, but the forecast is not great. So we're hoping to have an open dome tour tonight. And people are asking, there's some students in the audience tonight about the GMU ID. Hold on, we will get to the show in a little bit, but if you do have questions, you can paste them in the chat. To find out more information about GMU Observatory, if this is your first time joining us tonight, you can find us at science.gmu.edu/observatory. You can follow us on Twitter at GMU Observatory, and you can reach us via email at gmuobservatory@gmail.com. We are hosting these alternating Thursday evening under the stars. I crossed off stars and wrote dome because the weather's been pretty cruddy this semester, and we haven't had many opportunities. I'm hoping tonight is going to be one of those opportunities for us to open the dome and look at the night sky. Our next event is going to be in 2 weeks on the night of November 19th. At the end of tonight, or at any time, I do ask that you fill out a survey. That survey will be posted, the link to the survey will be posted in the chat shortly. The GMU Observatory is located atop of Research Hall on the Fairfax campus. You can see a picture of it here. Here's the classic telescope dome, one of the iconic structures we have here on our campus. We have a control room next to it, and this little building over here. And we have 2 monitors that we're going to be viewing tonight to view the night sky remotely and control the telescope from the safety of our own homes. We're glad to bring you tonight some programming, a break from the regular programming that some of you may have been watching over the past few days. And if you'd like to sign up for our monthly newsletter, The Moon, the Mason Observatory Outreach Newsletter, you can also sign up for that online. And in our last issue, we talked about some of the science discoveries that have been taking place in the clouds of Venus. We also have a philanthropic organization called the Patrons of the Observatory. When you become a patron, you become a part of a distinguished group of philanthropists, leaders, and educators. Your donations are tax deductible and provide critical support for observatory activities such as these, and engaging the broader Washington, D.C. community about the wonders of our universe. We have different support levels ranging from $50 a year for star individual memberships up to Big Bang memberships, and we'd like to thank our current and new patrons of the observatory. We have personnel I'd like to introduce. I'm the observatory director, Peter Plafchan, and we have with us tonight Professor Rob Parks, the deputy director of the observatory, Justin and William, who are our observatory graduate teaching assistants, Brandon Iverson, who is the president of our student club, Friends of the Observatory. So if you are a student here tonight, yes, Professor Parks is here tonight. We have a student club as well, and you can find Friends of the Observatory, or Photo for short, on Mason 360, and they would welcome more astronomy enthusiasts to come join. We have lots of exciting events. Right now we're actually having a logo design contest, and we'll get t-shirts for those who submit entries. Once again, you can contact us at gmuobservatory@gmail.com. Follow us on Twitter at GMU Observatory, and we'll post links to the survey in the chat as the night goes on. It is now my pleasure to introduce a colleague of mine, Dr. Luisa Rebull from the California Institute of Technology, Caltech. And yes, Dr. Parks' cat was here recently sighted. Dr. Luisa Rebull is a scientist at Caltech, and she is going to talk to us about the universe in the infrared, Spitzer's final voyage. I've had the pleasure of working and collaborating with Dr. Rebull. She's an amazing scientist, and I'd like to welcome her. It's one of the advantages of the pandemic, despite all the disadvantages, the opportunity to bring in some expert scientists virtually to come present to us. And so let's all give a warm applause. You can use the reaction buttons on your Zoom features to welcome Dr. Luisa Rebull. We will have questions at the end of the talk. If you'd like to ask questions during the talk, please post the questions in the chat. Dr. Rebull, I will turn things over to you.
Awesome. I think you do have to stop sharing, though. I guess I can force you to stop sharing. There we go. Okay, come on. There we go. All right. So yes, thank you so much for giving me the opportunity to provide you at least a little bit of a distraction from the rest of the week tonight. So what I'm going to cover tonight is I'm going to start at the beginning. I'm going to start with what is infrared, and then we'll talk about Spitzer, the spacecraft itself, and the engineering that went into it. And then I'll have some highlights of some of the big science results from Spitzer. It is going to be highly incomplete because, you know, I only have just so much time here. And then the last thing that I wanted to cover tonight is how you too can get access to some of the data. So NASA has a lot of space-based telescopes, but only 4 have been given the very special name of great observatories. And there are only 4. So Compton, and you can see they span the electromagnetic spectrum. In other words, they're covering light beyond the visible. So the Compton Gamma Ray Observatory observed in gamma rays. It is no longer with us. It's re-entered the atmosphere. The Chandra X-ray Observatory is still observing. Hubble observes in visible light, and it's of course still working. And then there's Spitzer that observed in the infrared. It is sadly no longer working. So the reason astronomers need telescopes spanning a large range of wavelengths is because we're studying, for the most part, places we could never ever visit or even get close to. So we have to take advantage of all of the information that we get from these objects, which includes light at a myriad of wavelengths. So this is the same little galaxy at several different wavelengths. So we've got, on the left, you've got X-rays. And so this data was taken with the Chandra X-ray Observatory. There it is in the ultraviolet. This is using a satellite called Galax. There it is in the visible light. That's an image taken with HST. Then this image is in the near infrared. You could use some ground-based surveys like TUMAS, or you could use Spitzer to observe in the near infrared. And then far infrared, you could use Spitzer or another spacecraft called Herschel. And so if you look across these images, they're all oriented the same way, they're all on the same scale. There are things that are bright in some wavelengths that are dark at others. And it's clear that we're looking at very different things when we look at the different wavelengths of this same galaxy. So the light is very different. So Chandra X-ray light, X-ray photons are like 2 nanometers in length. So like a billionth of a meter is a nanometer. And so we're looking at things that are typically very hot. If it's thermal emission, we're talking like 1,000,000 Kelvin. So we're talking like black hole accretion disks in the X-rays. In the ultraviolet, the wavelengths are like 200 nanometers. The temperatures are typically maybe 5,000 or 15,000 Kelvin. And these are usually the hot stars, which are also the young stars. In the visible light, you're looking at things that are about 500, or the light itself is about 500 nanometers in wavelength, or about half a micron. A micron is a millionth of a meter. And you're looking at things that are typically 6,000 Kelvin, kind of like our sun. And that at that temperature, you're looking at sort of the run-of-the-mill stars, just like our sun. In the near infrared, you're looking at the wavelengths of light that you're using is like 1,600 nanometers or 1.6 microns. You're looking at things that are maybe 2,000 Kelvin. These tend to be the very cool stars, which are usually the old stars. And then the far infrared, the wavelengths of light are like 100,000 nanometers or 100 microns. You're looking at things that are typically 30 Kelvin. And that is typically the cool dust that is heated by the hot stars. So you're looking at very different physics, very different astrophysics, very different processes across all of these wavelengths. But I work at IPAC, and at IPAC, we have a very biased view of the electromagnetic spectrum. We tend to focus on the infrared because, let's be honest, that's the coolest part of the spectrum. So here's a little dog. On the left, there's a picture of him in visible light. And on the right, there's a picture of him in infrared light. And so there are some very important things to note about this. One important thing is that I have translated the infrared light into light that you can see. Sometimes this is called false color imaging. But let's be honest, words are important, especially now. Words matter. And false color makes it sound like I'm hiding something. So I much prefer the term remapped color, because what I'm doing is I'm mapping the infrared colors into light that we can see. Because remember, a true color infrared image is super boring because you can't see infrared light. So you have to translate those infrared light photons into light that you can see. Now, the other important thing is that the way that I'm going to do this corresponds to a temperature scale that you see here on the right-hand side. So things that are cool are black or purple or blue. Things that are hot are going to be white or yellow. So you can see that his water dish is cool. The fluff around his head is cool. His ears are warm. His face is warm. But because he's a healthy little dog, his nose is cold. So now you know that hot things glow in the infrared. What do you think that's going to look like? Just take a minute and think. What do you think it's going to look like? Which one is the hot water? If you said the one on the bottom, you're right. You can see that the hot water is heating up the base of the faucet and even the sink basin. And you might be able to see on your screen that the base of the cold water faucet is still cold, even though the hot water is on. Okay, so indeed, yeah, the bottom one is the hot water. So what do you think that's going to look like? I can tell you the hairdryer is on. That's what it looks like. You can see really vividly the heating elements in the hairdryer and even the turbulence and the hot air that's coming out. So now you know that infrared can reveal things that are totally hidden in visible light. It also turns out that infrared can see through some things that are totally opaque to visible light. Here I have just a regular garden garbage bag, and you can see straight through it in the infrared. It turns out that you personally are extremely grateful for this property of infrared light, because if you are unconscious in a burning building, the way that the firemen will find you is with an infrared camera. Most fire departments, at least the larger ones, have an infrared camera somewhere in their arsenal of gear, because it is really, really powerful for finding people in smoky buildings. It turns out lots of police departments have infrared cameras too. So I live here in Southern California in the foothill communities, which means that the suburb I live in is up against the hills. And the hills, well, you know, we get all of our rain at once in the winter, and then the rest of the year it just bakes. So we actually have something called fire season, and the infrared cameras on the helicopters are a critical firefighting tool, because it's looking for hot spots in the hills of fire that you need to go put out. It turns out it's also useful for finding fugitives. Not too long ago here in LA, the temperature got up to like 120 in the daytime. And then not long after sunset, some idiot was running away from the cops up into the hills. And they use the infrared camera. And normally when you're using an infrared camera, just like you see here, the person is warm compared to the background. But when you're running through rocks that have been baking in 120-degree heat all day, it turns out you're cooler than the rocks. It's really rather dramatic. But at any rate, infrared can see through some things that are totally opaque to visible light. But there are some things that are transparent in the visible that are totally opaque in the infrared. So right here I have a set of French doors that are in my living room. The one on the left is open, the one on the right is closed. And you can see that you can see me through the window, but not in the infrared. The infrared doesn't make it through the window. And this, incidentally, is why when you park your car in the sun in the summer, you have to start driving like this when you get back in the car, because all the optical light from the sun gets through your windows, heats up the inside of your car, and then the car re-emits in the infrared, but the infrared can't get out. So it just bakes and bakes and bakes. So the next time you can't touch the steering wheel, think about all of the infrared that's stuck in your car. So now all the pictures I've shown you so far comparing optical and infrared have been things you might encounter on a daily basis. Now we're going to leave that a little bit. Here I have something that astronomers call a dewar. It's really just a fancy name for a thermos bottle. And I've got liquid nitrogen in it. So on the top, I've got liquid nitrogen inside the dewar, and there's the picture of it in the infrared. And the nitrogen is 77 Kelvin. So it's much colder than the camera can register. So it just gives up and colors it all black. But now I'm going to put frozen peas in the liquid nitrogen. Now the frozen peas are cold, but they are not 77 Kelvin cold. They are warm compared to the nitrogen. So the infrared camera can see them. And that is exactly what's going on in space. Even though some of the things we observe in space are very cold, they're warm compared to the background. So it's easy to find them in the infrared. This is the everyday constellation Orion that most people are familiar with in one way or another. And this is obviously in the visible light. That's infrared. How much you miss if you stick to just the visible. You might know that the Orion sword is a massive stellar nursery, but I bet you didn't know the belt had forming stars too. And you can even see a big circle around Orion's head. Circles like this, when you find it in the nebulosity and the fuzzy stuff in the sky, almost certainly means something exploded. So there's almost certainly this is representing the death of a star that used to be near Orion's head. So why do we have to go to space to do infrared astronomy? Well, there's two really important things. One is that space is cold. If you're trying to measure tiny bits of heat, your telescope has got to be cold. If you do things right, sometimes you can observe in infrared from the ground, but the best analogy is someone trying to ask a question. So the best way that I can explain this is if you're trying to observe in the optical, but with a telescope made out of those long cylindrical fluorescent bulbs, because in the infrared, your telescope is the same temperature as the air around you. So it's glowing in the infrared. So you have to observe very, very carefully if you're going to observe from the ground. So by going to space, you get rid of that problem because space is cold and you can cool down your spacecraft really efficiently. The other big reason to go to space is that the atmosphere absorbs a lot of infrared light. So the cartoon that I have here is transmission. In other words, how much of the light gets down to the ground, represented by the brown line there, as a function of wavelength. So if you are a gamma ray astronomer, an X-ray astronomer, or an ultraviolet astronomer, you have to go to space. You don't have a choice because that light does not make it down to the ground. The visible light, of course, makes it down to the ground, and you could observe from the ground. If you pick your site very wisely, so it's very high and very dry, and you pick your wavelength of infrared light very carefully, you can do some infrared astronomy from the ground. But all of these absorption lines affect the amount of infrared that makes it down to the ground. And those absorption line comes from really useful things like oxygen and water, all things that we need to live. But it makes it really hard to do infrared astronomy from the ground. You go to longer wavelength light, and you have to go to space. Again, it just doesn't make it down to the ground. Radio light does make it down to the ground, so you can do radio astronomy from the ground. So this is Spitzer's launch. It was launched from Cape Canaveral in Florida in August 2013, or 2003 rather. It's more than 16 years ago now. I should update the slide. If you've never had the privilege of going down to Florida for a launch, it is very exciting and very impressive, but all of the stands and things that you see when you see pictures of people visiting launches, they're optimized for manned mission launches. So the unmanned missions don't have those kinds of stands that make it easy to watch. And it turns out that the best place to, from the launch pad that Spitzer was using, the best place to watch is not actually on base. It's actually on a fishing pier just south of the Cape. And so this is really what it looked like. So a half a dozen really annoyed fishermen at 2 o'clock in the morning, and at least 100 astronomers screaming, go, 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 as Spitzer launched. This really is what it looked like. So why is the spacecraft named for Spitzer? Well, Spitzer, so in recent years, NASA has taken to naming spacecraft as a result of naming competitions. You can submit your submission in a couple paragraph justification, and they picked this name from more than 7,000 entries into this contest, and it was named for Professor Lyman Spitzer. And he did a lot of really amazing things, but one of the things that I really remember is that in 1946 he was the first one to propose putting a telescope in space. I mean, think about that. In 1946, the only things that we had that really could be called rockets were German V2s. And he had the vision to say, let's not put a bomb on top, let's put a telescope on top and see what we can see when we get outside the atmosphere. And he was a primary force behind getting Hubble funded and launched. It turns out he also studied the interstellar medium. So in other words, the stuff between the stars, the fluffy stuff that we can see so easily with Spitzer, the telescope. This is Spitzer the spacecraft. And so when it was first designed, it had this design on the left-hand side. So you see it's a relatively large spacecraft, and the entire telescope is inside a bath of cryogen. So like the Dewar, the thermos that I was showing earlier, in order to try to keep the telescope cold, this original design had the whole telescope inside this bath of liquid helium. But now, the design that actually flew is on the right-hand side. There were a lot of really clever engineering decisions that went into this. The telescope between these two is exactly the same size. So you get the same amount of light collecting ability, but the spacecraft itself is much smaller and much lighter, and it has to carry much less cryogen. It also turns out to be much easier to test as well. So this was a revolution in our ability to actually get Spitzer funded and off the ground, was all of this clever engineering that went into it. This is Spitzer the spacecraft here on the right. You can see it's not very big. You can see the scale from the people who are working on it. This is the side with the solar panels. So it's the side that always faces the sun. Then behind the solar panels, this is the telescope itself. So the light comes in from up here, and the telescope mirror is here. The instruments live in there. And then the cryogen lives down here. Now, this side of the telescope is painted silver, so that any little bits of heat that make it past the solar panels get reflected back. And then the far side of the telescope is painted black, so that it passively radiates away into space. And it cools off very efficiently with this design. So now I'm going to have a whole series of screen snapshots from to demonstrate the different orbits that these various satellites have. It actually comes from a web application called Eyes on the Solar System. If you have not discovered this, you should go play with it. It's really cool. It allows you to zoom around the solar system, speed up time, slow down time, move back in time, forward in time, and see where all of the spacecraft in our solar system are. So I just have a couple of screen snapshots here. So this is Hubble, the Hubble Space Telescope. It is in low Earth orbit. So you can see from Hubble's perspective, the Earth is really, really big. And it turns out that Hubble spends a significant amount of time each orbit simply trying not to look at the Earth because it is so big and occupies so much of the sky from Hubble's perspective. There are a lot of satellites in low Earth orbit. These are just a few of the satellite trails that are moving around in low Earth orbit. As we zoom out a little bit, this is Hubble's orbit here, but we can see more of these low Earth orbiting spacecraft. But where do the other telescopes live? This is Chandra, the Chandra X-ray Observatory, and it orbits in a long elliptical orbit. It goes about a third of the way to the moon on every orbit. So it's got this long elliptical orbit that, you know, enables it to move away from the Earth for a little while, but then come back again. So we're going to zoom out even further. You may be able to see on your screen these two satellites called the Van Allen satellites. These two satellites were specifically launched to study something called the Van Allen radiation belts. And the Van Allen radiation belts are clusters of high energy particles that are trapped in the Earth's magnetic field. And the reason this matters is that if you are trying to observe things that are very far away, you want to avoid sending your spacecraft through the Van Allen belts as much as you can, especially for Chandra, where the spacecraft is designed to focus high energy photons. All of the engineering that goes into the Chandra telescope also focuses high energy particles. So when Chandra happens to go through the Van Allen belts during its perigee, its closest pass to Earth on an orbit, then it really takes a hit from the radiation. And so that's something that the Chandra telescope has to deal with when the orbit lines up with the Van Allen belts. We're going to zoom out even further. We still even haven't found Spitzer. This is more or less now, and you probably can't read it. There's Earth up at the top. There's Kepler. You may have heard of Kepler. There's Spitzer here. There's the sun. So the Earth is here, and Spitzer is all the way back here. There's the sun and Mercury and Venus for reference. So Spitzer is in a solar orbit. It's orbiting the sun just like the Earth is. Right after it launched, we kicked it out of the Earth-Moon system, and it's just been slowly trailing away from us over time. So it's actually quite a ways away from us now. So the main things to remember about all these orbits is that Hubble orbits Earth very close to Earth. Chandra orbits Earth, but in a long elliptical orbit. Spitzer orbits the sun, not the Earth. And Spitzer is slowly trailing away from us. And this orbit that Spitzer has is really, really good because unlike Hubble, we do not have to spend a significant amount of time simply trying not to look at the Earth and the moon. I mean, we still don't want to look at the Earth and the moon, but it doesn't dominate our view of the sky because we're so far away from the Earth and the moon. Also, by getting so far away from Earth, we don't have to worry about the Van Allen belts. There's no damage to the detectors or the electronics that comes from that harsh radiation environment. And by getting away from the Earth-Moon system, it's really easy to cool off. It allows the telescope to just passively cool and get down to quite low temperatures. So that's why Spitzer is in this orbit, and cool is absolutely critical. So it was launched in August 2003, and up until May 2009, it had a lot of cryogen on board, and that meant that it could operate at below 12 Kelvin. And it was supposed to have at least a 2.5 up to a 5-year lifetime. It actually lasted 5.5 years, which is pretty awesome. But because that orbit is so good, and because the spacecraft is so good at cooling off all by itself, we could continue to operate Spitzer at about 28 Kelvin, starting in July 2009. But we lost we lost 2 of the 3 instruments. And for the 1 instrument that we could still use, we lost half of the wavelengths. But those 2 wavelengths still work just like they did before. And we were able to observe between July 2009 and January 2020, just with those 2 channels. And believe me, we did so much really amazing science that's buried in that data. And it turns out then over the whole lifetime of Spitzer, we've got 16 years of data to mine. So just connecting all the dots here, the Earth trailing orbit, plus the fact that we need to be cooled, the spacecraft needs to be passively cooled off. And it turns out it has no moving parts that can break. But that means that in order for it to talk to Earth, it has to turn to talk to Earth. It can't continue to observe and talk to Earth at the same time. It has to turn its antenna towards the Earth. And because the original spacecraft was only designed to last 2.5 to 5 years, the antenna was only designed to communicate with Earth when it was relatively close to Earth, and it is no longer relatively close to Earth. So there is kind of a natural end to the mission. There's another view of the solar system. In this perspective, the sun and the Earth are stationary, and the Earth, and so Spitzer is just slowly trailing away from the Earth. And so right after launch, of course, it was right close to Earth, and it kept going, and then it ran out of cryogen about here, and then our 10-year anniversary was here. And at this point, you can see, so back here, it's easy to have the solar panels facing the sun and the antenna, which is down there facing the Earth. That's relatively easy. But by the time it gets out here, in order to have the solar panels facing the sun, the antenna is no longer facing the Earth exactly. And so in order to try to communicate with Earth, the spacecraft has to tilt enough so that the sun reaches the parts of the spacecraft that you would really rather not warm up. So it becomes very difficult to plan this. And it turns out that near the end of its mission, it was depleting its batteries. So, you know, like when we have your cell phone and you're trying to use the cell phone to get navigation somewhere and you're running out of battery and you're like, oh, please just hang on long enough for me to get where I'm going, right? That's what happened every time Spitzer needed to talk to Earth. It would start losing battery charge and it would communicate with Earth as long as it could. And then, oh, no, I got to plug in. So it would let go of Earth and face the sun, cool off, and recharge its batteries, and then it could go back to observing. This is an animation that is a visualization of this. So there's the sun over here, there's Earth. So near the beginning of the mission, it was easy for Spitzer to turn and talk to Earth, but keep the solar panels facing the sun. But the further it gets away, now in order to talk to Earth, it's actually starting to warm up the spacecraft and make it harder to charge the batteries because the sun is no longer face on the solar panels. So there was a natural end to the mission. So come on, next slide. Why is it not doing next slide? Okay, so what do we study with Spitzer? Well, you know, basically it can be summarized as the old, the cold, and the dirty. So we're looking at very old things, things from the very beginning of the formation of the universe. We're looking at very cold things, and we're looking at dusty things because the infrared is really good at seeing all of the fluffy stuff, all the dust and gas. So some of the cool results, I have some from the solar system here. So you know, of course, that Saturn has rings, but I bet you didn't know that it has an enormous, enormous ring. This is an artist's conception. There's Saturn in the middle, and you can see its famous ring system is pretty much within that pixel there. And it turns out it's got this enormous, enormous ring around it. And Spitzer's discovered this ring. It's very fluffy, very tenuous. Like if you were standing in it, you might not notice that it was there. But it's really only visible in the infrared. If you could see it with your eye, it's about 2 full moons across. It's huge, and it's not aligned with the rest of the ring system. It turned out that there was a prediction that this ring exists because Saturn has a lot of moons, but there are 2 moons that matter in the context of this ring. Phoebe is one of the distant Saturnian moons, and it orbits within it, and it is likely the source of the dust that's creating this ring. Iapetus orbits near this ring, and it is dark on one side of the moon. And so that's kind of like when you go on a road trip and you're driving along, your windshield gets covered in bugs, but not your rear windshield. The reason Iapetus is dark on one side is exactly that. It's going face first through this dust, and so it's dark on one side. There's Iapetus in there. And so that side of Iapetus is dark compared to the rest of the satellite because it's going face first through this dust ring. And there's Phoebe within the dust ring. Okay, some cool Spitzer results from our galaxy. So we learned a lot about galactic structure from Spitzer. It's really hard to study our own galaxy because we're in it. And people have asked me for years, well, how do you study it when you're in it? And I kind of struggled to come up with a good analogy. But my son, he's now 12, but when he was little, because our families are from the East Coast, so even when he was little, he had a frequent flyer number because we were flying back to see family. And it's not like we're in the good seats either. We're back in the cheap seats with cattle, right? But in the plane, you know, he was sitting, he was so into flying. Oh my gosh, I thought for sure at that point he was going to be a pilot because when he was 2 and 3, he was so into planes. He was so excited every time I got on a plane. And so at one point, of course, he was sitting by the window to watch. And as we're getting ready to pull back from the gate, he starts smashing his face up against the window. I'm like, what are you doing? So I'm trying to see our pilot. That right there is the analogy that I was looking for to explain studying the galaxy when you're in it. So if you're inside the plane and you have to sit near a window, you probably have no idea what your plane looks like. If you've never been outside the plane, you have no idea what your plane looks like. But you can look out the window and see other planes. And you'd be like, okay, I can't see if we have a tail, but every other plane has a tail, so we must have a tail. And then if you happen to have a window in which you can see the wing of the plane, oh yeah, we clearly have wings. Well, we look out the window and some of the planes on the tarmac have like those like turn up bits at the end of the wings and some don't. And so you would have to observe your own plane's wings to know whether or not you had that little turn up or not. If you were trying to figure out where the pilots were, boy, that's hard. Right? Because you'd have to start by looking out the window and looking at other planes and go, oh, most of these planes have people in the front, so we must have people in the front. But it is so hard to see the people because not only are you back behind all the other passengers, but there's curtains and doors to the cockpit and what have you, and you really can't see your pilot from inside the plane. But infrared allows you to see through. So when you're studying the galaxy, infrared is super important because it allows you to see through the galaxy, to see close to the center of our galaxy, to even see past the center of our galaxy and start to explore the structure of our own galaxy. I mean, there were some things about it that we knew just from looking at other galaxies, but there was a lot that we didn't know. But by having access to the infrared, then we could start filling in the gaps. And Spitzer made huge strides in understanding what our galaxy looks like. So this is an artist's conception of our galaxy, looking down on the galaxy from above. And because we're humans, all of our coordinate systems are centered on the sun because we're very human centric. So the coordinate system that's here is centered on the sun. So we live in an arm called the Orion Spur, but then it turns out we live in a barred spiral. And so we've got these big arms that are coming off from this barred spiral. And Spitzer was the one that helped us flesh out. So this is the data that was used. So this over here on the right-hand side, you're looking at a cone that's sweeping through the galaxy, and the data that's scrolling by here is what that data looks like. So as we get close to the center here, that's the center of our galaxy scrolling past. And then it's going to keep going, and we're going to be able to see off to the other side of the center. So this program was called Glimpse, and it actually in the end observed a full 360 all the way around our view of the galaxy. So without a movie, this is what it looks like. So there's the galactic center. And then, so the part that runs off here picks up over here, and then it runs along here and falls off there, but picks up here. So you see it's like stripes of this long map. This is an enormous image. Like if you printed it out full resolution, it would circle the Rose Bowl, which probably doesn't mean much to you guys on the East Coast. You'll have to take my word for it that the Rose Bowl is pretty big. Okay, so another really important discovery from the infrared is that young stars have dusty disks. So in order to explain this, I have to back up a little bit. IRAS was the first all sky survey of the infrared sky. And whenever you have a new telescope or a new instrument, the first thing you want to do is calibrate it. And there's a star called Vega, which turns out to be the basis for all of the measuring brightness, the brightness measuring systems in astronomy pretty much all come back to Vega. And so Vega is almost always the first thing that you look at. And so IRAS, of course, was observing the whole sky. And so the scientists that were running IRAS pulled out observations of Vega, as well as several other standards. And Vega was bright. I mean, really bright. And certainly the popular conception of scientific discovery is like, eureka, you know, jumping out of the bath and running down the street. In my experience, that's not what scientific discovery sounds like at all. In my experience, scientific discovery sounds like, huh, that's weird. How could I have screwed that up? Huh. All right, well, let me keep going and see what I can do. And so for IRAS, they had not just Vega, but about a dozen total stars that were too bright. They couldn't figure out why those stars were bright. It didn't make any sense to them. They said, you know, they were like, we must have screwed something up. Let's do the calibration with all the other standards that we have, and then we can move on, and then we'll circle back and figure out what we screwed up, why Vega is so bright. Turns out they didn't screw anything up. Vega has a big old dusty disk around it, which makes it really bright in the infrared. So what I'm going to show you is not an image from real data. It is an artist's conception. But this is almost certainly what Vega looks like when you get up close, because Vega is a very blue star, and it doesn't have a big, thick, continuous disk. It has a ring of dust that almost certainly has big chunks in it, but also lots of fine particles. So almost certainly this is what Vega really looks like. Dust, all that dust around it is why Vega is so bright. So this is the cartoon version of star formation. You start out with a big cloud of gas and dust. We're going to zoom in on one of the cores, and it collapses under its own gravity. Just because of the way the physics works, it doesn't fall straight in. It falls onto a disk first. And then for reasons nobody understands very well, but almost certainly involve magnetic fields, a fraction of that matter turns around and gets ejected above and below the disk, usually at the magnetic poles. And eventually that cocoon of matter gets blown away. Eventually the matter accretes through the disk onto the central star. The accretion rate slows, the jets turn off, and you end up with a disk that's forming planets. And then you end up here with a genuine bona fide adult mortgage paying star that's actually burning hydrogen with a planetary system. And you see all the planets are in a disk going in the same direction, just like our system. So these guys are like the toddlers, and these guys are like the teenagers down here, and these are the adults. So I just have a couple of images of each of these stages as revealed by Spitzer. So this is a clump of dark dust here, it's seen in the visible, of a thing that had been called the starless core L1014. But Spitzer looked at it and surprise, it is not starless. It has a baby star inside. It turns out to be a baby brown dwarf. So not a very massive star, but a forming star nonetheless, hiding in that clump. This is a slightly older star, again, still buried in the dust, but you can see that young star is there and it's got these huge jets coming off of it that you can't even see in the optical. You can only see them when you look in the infrared. Here is a star cluster called NGC 1333. And here in this color scheme, everything that's green is a jet. So there's a ton of jets because the stars in this region are just the right age to become jets. And so there's jets, there's arcs, there's clumps. And to make matters worse, the stars, of course, are moving. So some of the clumps have been left behind by the stars as they keep moving. So there are people who've made careers out of trying to figure out which one of these clumps goes with which star. So this is actually a Hubble image of M16, the Eagle Nebula. It's the talons of the eagle that you see here. And this is the most popular image taken by the Hubble Space Telescope. It's the most commonly downloaded one from their website. It's called the Pillars of Creation, because what's going on is you've got some bright young stars up above pushing around the gas and dust and probably prompting at least some star formation in these talons. So this image is actually really tiny. That is the orientation with respect to the background image, and that little footprint there is that footprint. So this image that's here is an image taken with Spitzer. So it's all infrared light, and you can see that the eagle talons there look very different in the infrared than they do in the optical. And you can see that it's part of this larger complex, and you see this red emission here. This is almost certainly leftover supernova. So almost certainly what has happened is that a supernova has gone off and is pushing around the gas and dust and ultimately will be crumpling those towers if you wait long enough. So this is some of my favorite data because it's mine. This is called the North American Nebula because you see here we've got North America. There's Florida, there's Mexico, there's the Gulf of Mexico, there's the Mexican Riviera down there. This over here is called the Pelican Nebula, and sometimes it's hard to see, but there's the beak, there's the belly. That's sort of the back of his neck. This is the same region in infrared. I swear to you, it's lined up properly, but it looks totally, totally different. The back of the pelican's neck, you can see, and the Mexican Riviera, you can see. And it turns out that dark Gulf of Mexico is a huge nursery of hundreds of forming stars. I'm the one who discovered them. So zooming in on that clump, there's hundreds of them, and they're all babies, and they're all furiously starting to build their planetary systems and start accumulating enough matter to start burning hydrogen and begin their lives as stars. I have only had images so far. Spitzer had a spectroscopy instrument on board, which spectroscopy is like a prism. It breaks up the light into like a rainbow, only in the infrared for Spitzer. And so here I have a plot that's brightness, the function of wavelength. So the one on the bottom here, the spectrum on the bottom, is of a big comet that visited the outer reaches of our solar system, came in close to Earth years ago. It's called Comet Hale-Bopp. You might remember it if you're old enough. And you can see all of this structure in this spectrum. This is a spectrum of the outer disk around this star with the relatively boring name of HD 69830. The bumps and wiggles in this spectrum are just like the bumps and wiggles in Hale-Bopp. So what that's telling us is that the constituents of Hale-Bopp are also the constituents of the disk around the star. And a lot of that texture comes from olivine. So olivine is like green sand beaches in Hawaii. It looks like this when you're up close to it. Okay, so Spitzer, I'm going to try to wrap up here. Spitzer and star formation. Spitzer has just phenomenally number of young stars that we know. So we have a much better understanding of the interaction between the clouds and the stars, how stars cluster, the time scales for all of those stages. And it turns out planet forming disks happen everywhere. And so that's not at all a surprise that we're finding that so many stars have planets. So I'll spend a couple slides on exoplanets. Spitzer was not designed to study exoplanets, but it turns out that it does really, really well. So Spitzer didn't discover planets, but it helps us characterize the planets. So I know that you had an exoplanet talk from Jessie Christensen not too long ago. So she probably covered some of this. So one way to discover exoplanets is looking for radial velocities. So as the planet goes around the star, the planet, if it's massive enough, tugs on the star enough that you can see it wobble. So like Jupiter in our solar system pulls on the sun just a little, enough that if we were someplace else, we could see our sun wobble. And so that's the radial velocity method. Spitzer doesn't do that. Transit photometry, you may have also heard of. So that's brightness as a function of time. And when the planet, in this cartoon, when the planet goes in front of the star, the brightness dips a little bit. And that tells you that there's a planet. There's also a way of discovering them using microlensing, which is where you observe from Earth against a dense field of background stars. You can see a star and planet system moving across your line of sight. And if you plan your observations just right, you can see little blips that are indicative of there being planets there. And if you're really good, you can do direct imaging of a star and planet, but that's really hard. That's like trying to take a picture of a mosquito that's orbiting a spotlight. It's really hard. So Spitzer was good at doing the transit photometry and the microlensing. So transit photometry with Spitzer, we're going to start this video here, and we're going to change our perspective so that now we're going to watch that planet go behind that star, not in front, but behind. Because it's Spitzer, it observes in the infrared. And the planet is cool, so that it emits in the infrared. And so most of the time when you talk about transit searches for exoplanets, you're looking at the planet going in front of the star. But with Spitzer, we're looking at the planet going behind the star. So that means that we're actually seeing photons from the planet itself, which is pretty darn awesome. This is the cartoon version. This is the real data. So again, brightness as a function of time. These are tiny, tiny, tiny little dips, but they're real and they're there. And that shows that we're actually seeing light from the planet itself. So one of Spitzer's famous discoveries is TRAPPIST-1. So this is an artist's conception where you've got this the star, this very cool red star in the middle, and then you've got these planets all around it. You can see that there's water vapor close in, there's liquid water here, and there's ice out here. So this is foreshadowing. So TRAPPIST-1 is a small red dwarf star. So it's an M8. It's very, very small. It's closer to Jupiter really than our sun, but it's only 40 light years away. It's very close. And so the reason it's called TRAPPIST-1, I mean, astronomers sometimes they're just not very creative about naming things. TRAPPIST is the name of the telescope network that was used, and this is the first planet that they found. So the people who were operating this survey reported in 2016 that they found 3 planets orbiting this star. And they asked Spitzer for 6 hours to observe this star because they discovered it in the optical, but it's going to be easier to see in the infrared because the planets are going to be much easier to find around this very red star if you look in the infrared. So this is what they came to Spitzer with. They said, okay, well, we know that there's 2 planets around this cool M dwarf, and we think there might be another one out here, but we're not sure. Our data just aren't good enough from the ground. So they got a bunch of data from Spitzer, and it's weird. Huh, that's very strange. How could we have screwed this up? Let's go back and think about what we did again. Okay, seems like what we did is okay, but what would explain that? It's not at all immediately obvious. And they thought for a long time and they said, aha, I think it turns out there's actually a ton of planets around this star. So then they came back to Spitzer and said, okay, we need 20 days because Spitzer is just phenomenally stable, really good photometry and really good sensitivity. And so we can actually study this planet system really, really well. And so we at Spitzer worked really hard with these people to make as much of that 20 days be involved with science as possible. And they had contemporaneous observations from other observatories as well. So when they published in 2017, there are a lot of planets around the star. So the naming scheme goes, the TRAPPIST-1 is the star, and then B is the first planet, C is the next planet, and they discovered B, C, D, E, F, G, and H. So it actually is closer to a Jovian system, a Jupiter system, than it is to our solar system. This is a tiny little star. It's closer to being a Jupiter than a sun. And all of these planets in the TRAPPIST-1 system are really close to their host star. They're much closer than Mercury is in our solar system. So Jupiter is a much better analogy than the inner solar system for this system. So they came back to Spitzer and got 1,000 hours of essentially continuous Spitzer time. And so they studied these things really, really well. And so then in 2018, they were able to publish properties of these planets. We can tell the ensemble density. So so we have a much better sense of which of these planets have rock and liquid water and which don't. So we now know more about TRAPPIST-1 than any other solar system except for ours. So this is what the data actually look like. Here's brightness as a function of time. And all of the white stuff there are the observations of just the star. And all of these little dips are the transits of all of these planets. And sometimes they pile up on each other because these things are so close to each other that they tug on each other. So the orbits get synchronized, basically. And so you end up with transits on top of each other, which is why it was so hard to interpret those transits when they first got Spitzer data. So if you were able to stand on one of these planets, this is likely what you would really see because those planets are really close together. So they would be huge in your sky. This is actually one of a whole series of the Exoplanet Travel Bureau posters. Again, if you haven't found them yet, you should go Google that because they're really, really cool. Just in the few minutes I have remaining, gravitational microlensing. So this is where you are studying a background star and then the star and the planet go in front and the gravity pulls, distorts the light. And so you end up with a tiny dip on part of that light curve, which is what tells you that there's a planet there. So if you have just observations from Earth, when you work out the hairy math, it turns out there's a lot of the different but equally as good solutions. But when you had Spitzer at a much different location than the Earth, it allowed us to break that degeneracy. It allowed us to figure out exactly what the mass and distance was of these microlensing planets. So this is the very first Spitzer microlensed planet that was found. The white light curve is optical from the ground. The red is Spitzer data. And you see this shoulder there, and that's the planet. So in the last couple of slides I have here, we're going to go down a little bit of the digital rabbit hole because all of these data are your data too. All of the data are public. There's a website called Cool Cosmos, which has lots of pictures of the infrared, the world in infrared, and examples of how the infrared is used in everyday applications here on Earth, but then also has a history of infrared missions and examples of the infrared universe. So this is just a page from the infrared world showing how infrared gets used in other applications besides astronomy. And there's my last slide, which has a whole bunch of URLs that you can go. The first website there has a bunch of things, but including a bunch of videos that are called Irrelevant Astronomy. It's IR Relevant Astronomy, and those videos are award-winning. Some of them are really, really funny. There's the Universe Unplugged, which is also videos often that are very funny. They involve Hollywood stars explaining astronomy. There's a website specifically for the end of Spitzer. There's the Cool Cosmos website, which I mentioned. If you have a virtual reality headset, you can zoom around the TRAPPIST-1 planetary system. I mentioned the Exoplanet Travel Bureau. They have the posters, but there's also an interactive site you can explore. I mentioned the eyes on their solar system that's there. There's an app called NASA Selfie, so you can put yourself in space in front of some Spitzer images. If you want something more tangible, there's a book out written by Mike Werner, who was shepherding Spitzer since it was just an idea on paper. And if you're a high school teacher, you should Google NITARP and apply to come work with me and do real science with infrared data. So thanks very much for your attention. If there's any questions, Peter, I can take them now.
Thank you. I will clap for the 100 people we have in attendance. Thank you all. You can also use your reaction button to clap for our speaker virtually. I'd like to thank you for the wonderful, excellent presentation. And we are now going to transition into the Q&A portion of tonight's talk. So if you have a question for our speaker, please use the chat. I saw a bunch from earlier, so I'm going to scroll back through the chat and start asking you some questions, Dr. Rebull. So get there. We've already answered the question about the cat. So the students did appreciate your flex. You are the discoverer of entire groups of stars and baby planetary systems. How cool.
That seems to be what people want to know. They're like, did you get to name them? I'm like, yeah, but they're boring. They just have number names.
Yeah, those are your North American Nebula paper. Is that the one? Yeah, that's awesome. One second, we had a very active chat tonight.
I saw, I'm gonna let you weed through it though.
Yeah, the humidity is looking okay for now, by the way, but we might have some clouds coming up. There we go, almost there. Yeah, so we had a question. You showed a telescope that looked like an ice cream scoop. Do you know which one that was? There was I think it was your ground-based example.
Oh, maybe it was the telescope dome.
Yeah, I think it was the dome.
Yeah. So you guys are going to do a tour of the telescope later tonight, right? Of your telescope?
Yeah, we'll get a look at that one later.
Yeah.
So
for this one, yeah. So the telescope lives inside the dome. When you have cartoons, people like to draw it with the telescope sticking out. That is bad news. You do not want your telescope sticking out of the dome because you want to be able to close the dome and protect the telescope from humidity and rain and ash here in Southern California. So the telescope never pokes out of the dome. The dome opens and the telescope looks out. And then when you're done, the dome closes.
Yeah, this is my dumb joke about California. California seasons are like Taco Bell sauces, mild, hot, and fire. So we don't have to worry about ash so much here. So here's the next question. And you answered part of this during your talk, but the second part is an interesting question. Was Spitzer lost in space or did it come back? Have we ever brought back a space telescope before they stopped working?
So, okay, so let me go back to some of the orbits. So remember that Hubble is in low Earth orbit. And one of the reasons it was in low Earth orbit is because the shuttle orbited in low Earth orbit. And so because, that was by design so that you could go up with the shuttle, pick up Hubble, fix it, upgrade it, and let it go again. So that's why it's in low Earth orbit, because it was designed to be serviceable. So when you're in low Earth orbit, if you're in the right kind of orbit and you have the right kind of spacecraft, we're no longer running the shuttle. So we can no longer service Hubble. We can no longer go and get it and bring it home. It is out there to stay. So that's all of these unmanned missions are out there to stay. So the rovers don't come home from Mars. There's a very heartbreaking several stories of the, people writing from the perspective of the rovers of, don't I get to come home now? Haven't I been a good rover? All of these spacecraft stay where they are. So the Hubble in low Earth orbit, when you're in low Earth orbit, it turns out that you can lose orbital altitude because the atmosphere puffs up in response to solar heating, solar flares. And so when the atmosphere puffs up, the atmospheric drag increases. And so these things fall slowly back to Earth. And so you do occasionally hear about low Earth orbit satellites re-entering because of that problem. When you have spacecraft like Chandra that go far away from the Earth, or like Spitzer that are way far away, you don't get to go and get them. And I used to joke in these public talks about, oh, well, someday there'll be a space archaeology department that can, because eventually it's going to loop around and come back kind of close to Earth. And so I used to joke about it. Turns out there really is a Department of Space Archaeology at NASA. They're already starting to worry about how do we preserve the sites on the moon where Apollo 11 landed? How do we preserve where these various rovers finally stopped working on Mars. How do we preserve these things? So there is actually people who do space archaeology for a living, and I had no idea. But we do eventually, I mean, the space junk that's out there, we do eventually come back to, because I mean, several years ago now, there was an announcement of, oh, we found this potentially hazardous asteroid that may be coming really close to the Earth. And so people turned all their telescopic resources to it to try to figure out what it was. The spent second stage from an Apollo rocket that had finally come back around and was revisiting the homeworld. So of course it didn't hit us, and it's fine. But the point is that we will eventually catch back up with Spitzer. And maybe by then we will have enough technology to go out and get it. I don't know.
Yeah, I had the fortune of going to the Smithsonian Air and Space Museum, which we have here in DC, and I was there with someone who shall remain unnamed, and they asked me how they got the Mars rovers back from Mars, and the truth is those are copies.
Those are the engineering
and
copies.
we actually build a lot of these copies because they're actually really useful for simulating
testing,
the conditions and testing.
Yeah. I probably should have mentioned that I grew up in Arlington and I went to William and Mary, and my sister went to Mason. And so the Air and Space Museum is one of my all-time favorite museums, always has been.
Great. So. Yeah, I did not know that. Learned something new today. So what is the best place in the solar system for an infrared telescope observing deep space?
Away from the Earth. So basically where Spitzer is. So James Webb is going to move to a Lagrange point. That's the next big satellite telescope that NASA's going to launch. And that will be moving to a Lagrange point. So if you do the hairy math involving multiple bodies in space, there are some relatively stable points called Lagrange points. And so the James Webb is going to go to one of these Lagrange points, and that's also really good for infrared astronomy because you're away from the Earth Moon system. But the Spitzer orbit is actually a really good one.
Okay, so that's a good, yeah, it is, because just getting away from the Earth. Mm-hmm. Would it be beneficial at all is related to another question we received, to send a telescope outside the solar system? And maybe that would be a good opportunity to talk about kind of what NASA has planned next for future missions out in space. So
it is hard because, to paraphrase Douglas Adams, space is big, really big. You wouldn't believe how vastly, hugely big it really is. And so the earliest spacecraft that we have launched on their way out of the solar system were the Pioneer spacecraft that went past some of the larger planets, and then the Voyagers that went famously past some of these planets and sent back spectacular pictures. But those spacecraft were out of the Pioneers and Voyagers. I believe we're only in contact with one of the Voyagers now. And it made the news recently because they refurbished one of the Deep Space Network dishes that enabled us to reestablish contact with that one Voyager spacecraft that still has enough juice in its batteries to talk to us. But it is whispering, man. It is way the heck out there. And so the Voyager spacecraft, both of them are probably outside the solar system now, but it is hard, right? Because it takes a long time. Those things were launched in the 70s. It takes a long time to get out there, and those spacecraft are booking, man. They're not plodding along. It's just the distances are really, really, really big. And it is hard to maintain communications. It's hard to maintain power when you're out that far. So I don't know of any plans, but I'm sure there are really creative engineers who are trying to figure out solutions to that. But the next, like I said, the next big telescope that NASA is going to launch is Webb. And that one's going to stay in the solar system, but go to one of the Earth-Sun Lagrange points.
All right, great. Our next question is a bit of a dovetail to science fiction in the movies. Is The Martian a realistic movie, in your opinion?
So I think so. I think the guy, let me put the URLs back up in case people didn't get to copy them earlier. I think the guy that wrote it worked really, really hard to be as realistic as possible. But I tend to work with space robots. I am a fan of NASA's manned missions. I mean, that's what I grew up learning about and being very excited about. But I get motion sick at the drop of a hat, man. I can get motion sick in a freaking movie theater. So I am definitely not astronaut material. So I am just a fan of the manned missions. I don't know a lot about them, but from what I understand, the people that do know think The Martian is really accurate. The movie itself, because my husband is also an astronomer, and we were in the movie theater when that we were watching The Martian, and they put up something that was supposed to be JPL, and we just broke out into loud hysterical laughter because JPL is much more mundane in reality compared to the glossy glass and steel buildings that they showed in the movie. So yeah, as usual, Hollywood jazzed it up a little, but Yeah.
You do get to interact with Hollywood a little bit. You mentioned some of the outreach videos and the Universe Unplugged videos.
Yes.
Can you talk about some of the recent celebrities that you've had doing science at NASA and
So Will
JPL?
Wheaton, yeah. So Will Wheaton, who is this, is part of the Star Trek universe, has done several different movies for us, and some of the actors from The Expanse were also involved in some of the recent movies. So yeah, so you'll have to go check out the website. There's lots of cool videos buried in there.
Yeah, and then we've had some conversations going on in the chat, and it's about Starlink, and if Starlink's been affecting views of the night sky of ground-based telescopes. Is there an issue with
Absolutely.
orbital debris getting in the way of ground-based telescopes when they want to view specific objects?
So orbital debris in the classic definition is relatively small. So there's things, so the military tracks everything that's in space because it matters if you might run into them. And so I think some of the smallest stuff they track is like there's an astronaut glove that somehow fell out of the airlock in one of the Gemini missions. And so that has its own orbital coordinates and its own number because it's a piece of space junk. And so I don't know how much smaller than that they track, but yeah, so we're talking like size of a glove or smaller. So they try to keep track of all of those things. So if you remember that movie with Sandra Bullock that had the whole plot revolved around two satellites hitting each other and then creating havoc, that could happen, and it could be bad, because if you get all that debris, then yes, you can have a big mess when it hits other spacecraft.
Is that the Kess syndrome or something like that? Yeah, or effect.
I don't remember. Gravity, I think, is what it was called. So there were
Gravity's
parts
the name
of
of the movie.
Yeah,
Gravity's the name of the movie, but there's actually a theory behind that cascading collision, but we're not quite at that point.
Right. But
So
yeah. So, but in terms of the satellites, the suites of satellites, those are big, and the first generation of them were shiny. And so, yes, it's really bad for ground-based astronomy. The companies for the later generations have promised to make them black rather than shiny, which should help a little. But yeah, it's still an issue. There was a meeting a couple of months ago that brought together some of the people from those companies that want to launch those suites of satellites, the International Astronomical Union, various government representatives all got in the same room. Well, no, they didn't. They got into the same Zoom room for several days, and they wrote some really nice white papers that address all of these kinds of issues, both in terms of networks of satellites for ground-based optical astronomy, but also 5G cellular connections and radio astronomy. And there's implications for that too. So if you Google dark and quiet skies, you'll find the conference website that goes with this. And you can read the white papers and look at the presentations that were made, because they're looking at dark skies, but also radio quiet skies. So that's why you want to Google dark and quiet skies.
Great. So we have a lot more questions, and we are going to start our telescope show soon for everyone that's been joining. So let me ask the next question, and then we'll have you stop sharing your screen so one of our students can. The next question is, what human-made object is currently farthest away from Earth?
Think of the Pioneers, one of the Pioneers.
Yeah,
was
Pioneer
the furthest
probes.
one.
And the next question, what makes the Lagrange point so good? We heard Lagrange point a lot. What is that?
So it is college level math. So it's like freshman or sophomore college level physics. But you have to work out, if the simplest thing to imagine is just one mass, right? So if you have the sun and a planet, it's pretty easy to simulate that as just a tiny particle orbiting a big mass. And then the math is relatively straightforward. But when you start worrying about keeping track of where the masses are, and when you introduce additional bodies into the solar system, the math becomes hairier, and you end up having to calculate the gravitational field in multiple dimensions. And so you end up with these, I don't know how else to explain it, Peter. You're closer to the classroom than I am. Do you have an easy way of explaining how you end up with the minima where you do?
It's a bit of a balance point, right?
It's where the forces equal out.
It's a balance. Yeah. If you
and
think
so the
of things
spacecraft
like
that go out there, and the spacecraft that go out there don't just sit in the one point. They do Lisa-Ju figures, right? And so they're like tracing out basically like figure eights as they're orbiting the Lagrange point. Yeah, that may be more than I can try to explain using only voice in just a few minutes.
Yeah, no, that's great. There's often a common misconception about there being no gravity in space, but
Oh yeah, no.
yeah.
Yes, my kid, when he was in preschool, taught his preschool teachers that yes, there is gravity in space, because how else would the moon orbit the Earth if there wasn't gravity in space? How would the Earth stay in orbit around the sun
And
if there wasn't gravity in
and
space?
right, when those astronauts are floating in, they're falling. They're constantly falling, except they're falling in such a way that they keep missing hitting the Earth, and that's basically what an orbit is.
Yeah.
So we now have on the screen a view of our night sky. So I'd like to turn things over to our student tour guides to introduce themselves and tell us about what we're looking at. You continue joining us, Luisa, if you're willing to stick around. If you have any more questions, please continue to post them in the chat. And for now, I'll turn things over to our students.
Okay, thank you, Peter, and thank you, Luisa. I hope you all enjoyed the talk. I know I did. So we're going to go ahead and move on to the virtual tour part of the evening. So right now we're actually looking at a globular cluster M15, and we're going to come back to that in just a second. But first, in case you're not familiar with our telescope, if this is your first evening under the stars, I want to orient you a little bit. So right now we are remotely connected to a computer on top of Research Hall, which is a building on GMU's campus. And what we're looking at here is a view of the rooftop, essentially. So right now we're currently connected to this computer on the left here. So student observers will spend most of their time in this room collecting data and whatnot. Down here, you can see an outside view of the roof. So the telescope is inside this dome right here. So for reference, the door frame is about 6.5 feet tall. And last but not least, we have the actual telescope. And all of the images you see tonight will be taken with this telescope and with this particular camera. It's a little hard to see, but it's a little black kind of box there. That's the filter wheel, and then the camera itself is being covered by that filter wheel. So this is our setup. I know I went through that kind of quickly, but the humidity is probably not going to cooperate for very long, so we want to show you all as many interesting objects as we can. So without any further ado, I'll go ahead and put back the M15 cluster, and I'll let Owen tell us about it.
All right. Hello. My name is Owen. So what you're looking at right now is Messier 15. So it's one of the objects in Charles Messier's catalog of about 110, I think, objects. And so it's a globular cluster in Pegasus. And so a globular cluster is a cluster of stars, but it's not just like 3 or 4 stars. It's tens or hundreds of thousands of stars. And so if you were in towards the center of one of these clusters, your night sky would be very, very bright. One interesting thing to note about Messier 15 is that there is a planetary nebula in this globular cluster. You can't really see it with our telescope because the nebula is really small, and I don't think we took a long enough exposure. But Messier 15 was the first, I think. It's the first globular cluster to have a planetary or nebula inside of it. So that's fascinating. That's anybody have any questions or anybody want to add anything?
So I don't Well, there might be a few questions coming into chat in just a minute here, particularly about the telescope itself, which I can answer in chat in just a moment. But thank you, Owen, for the great description of globular clusters. And one thing I would like to just add is that even though the space that we're looking at looks very, very dense, and relatively speaking, it is, but as it was said earlier, space is still very, very, very big. And I'll never forget one of the problems I did in one of my undergrad astronomy classes, where we were actually calculating the probability that if we were in a rocket ship and we were somehow randomly oriented in the globular cluster, if we just went in a straight line to escape the globular cluster, what's the probability that we would run into a star? So if we're in the heart of a globular cluster randomly oriented and we go in a straight line, how likely are we to hit a star? And it turns out the answer is you might as well forget about any impact with a star whatsoever. The probability that you're going to escape without crashing into a star is pretty much certain. So even though the spacing, looks very, very dense here, relatively speaking it is, but still there's a whole lot of empty space between those stars still. Anyways, I think we're going to go ahead and move on to the next object. So Ashley, if you want to take us over to Mars, and while the telescope is slewing, what we can do is go back to any questions for Luisa. I don't know if Peter, you want to pick up where you left off, or if we want to just watch.
Well, unfortunately, our speaker had to get dinner. Our speaker just had to go get dinner.
Oh, okay.
So apologies, my internet connection is a little bit unstable tonight, apparently. But we will continue taking questions about the telescope tonight, and you can watch the telescope moving right now on your screen. And yeah, so our speaker's from the West Coast, and it's 6 p.m. there, so it's dinner time. So she had to go have dinner. So it was a wonderful pleasure to have her, and it was great to hear her talk tonight. And we will be continuing to show you a few objects tonight. I'll turn it back over to you, Will.
Okay, wonderful. Thank you. So we just saw the telescope slew to Mars, and we'll see that the dome is now turning in the background. So we'll need to take an exposure as soon as the shutter aligns with the telescope. So lots of questions about the focal length of the eyepiece, and we aren't exactly using an eyepiece here, yeah, so. Yeah, that's what I would say. Just write the focal ratio of 7.1. So why not move the dome and the telescope at the same time? Yeah, good question. So I don't particularly have a good answer other than I think it's just logistically easier for the software to move one thing first and then the other, but I don't have a really better answer beyond that. So the telescope is a reflecting telescope. The optical design is a Ritchie-Chrétien-Cassegrain reflector telescope. It's a mouthful, I know, but it's basically just a telescope that uses mirrors that are slightly curved. So the Ritchie-Chrétien referring to how the mirrors themselves are curved. And then the reflector part refers to the fact that we're using mirrors instead of lenses. So refracting telescopes use lenses, whereas the reflecting telescopes will use mirrors. And it's actually a lot easier to make giant reflecting telescopes than it is giant refracting telescopes. So the aperture of the telescope is 32 inches in diameter. And that's just the size of the primary mirror. which we can show you at the end if there is interest for that. But it looks like we have our target in view right now. So Ashley, why don't you tell us what we're looking at?
Yeah, thanks, William. So I'm Ashley. I am a senior here at George Mason University, and I am not an astronomy major, but it is one of my hobbies, and I'm going to be telling you guys a little bit about Mars. So we are looking at Mars. You guys may be wondering, Mars is supposed to be a red planet. Why doesn't it look red right now? Well, that's because our CCD camera takes images in black and white. It does not take color images in real time. But so what we can do is we can take a bunch of different images in a bunch of different filters in this filter wheel you see here, and we can stack them on top of each other to make a color image. But yeah, so right now you guys are looking at Mars. I'm going to give you guys a little bit of background on Mars. It's the fourth planet from the sun and the second smallest planet in our solar system, only being a little bit larger than Mercury. As I said, it's often called the red planet. That's because of its red color that we usually see in photographs and things that we might see on the internet. And that's because of the rich composition of iron oxide, which is really rust, which is in the soil, which is what gives it that red color. So yeah, Mars also has a atmosphere that is mostly made of carbon dioxide. And it is believed to have once actually had an atmosphere very similar to Earth's. But since then, it is believed to have been stripped away due to solar flares, and Mars actually does lack a strong magnetic field like Earth has. So it's believed that these solar flares kind of stripped away at the atmosphere and made it more CO2 atmosphere. But yeah, you can kind of see some gradations in color here. You can see a little bit of white areas, a little bit of gray areas, darker areas. That's actually some of the features that you might be able to see on Mars. Mars's surface is covered in craters, mountains, valleys, canyons, etc. And it is also capped by two large polar ice caps on the north and south poles, which are mostly made of water ice. Now there was a big debate whether Mars had water or not. Well, it does have these ice caps, but they are so frozen solid that it would be unlikely that we could harvest water from it without a large expending a lot of energy for it. So it would not be worth it. But one of the more impressive features on Mars, which I don't believe we're going to be able to pull up, the weather isn't quite ideal tonight, so that's why Mars may look a little blurry. But one of its more impressive features is actually an extinct volcano called Olympus Mons, which is the largest volcano and the tallest mountain in our entire solar system. And that is to say that it is 14 miles high, and the mountains Everest and Mauna Kea here on Earth are between 5 and 7 miles high. So if you think about it, Olympus Mons is actually double that. So it is the largest structure. It is the largest land structure in the solar system. But yeah, and then to round out Mars, it actually has two small moons, Phobos and Deimos, and that is all I have on Mars. Yeah, if you have any questions, post it in the chat, and I'll hand it back over to William.
Whoops, I was muted. So thank you, Ashley, for that great overview of Mars. So one thing I inevitably have to comment on is that you'll notice that Mars just kind of looks a little bit blobby. You can see some darker features and lighter patches, like Ashley pointed out. And a common question is, why doesn't it look a whole lot better? And that's a very valid question. So what's happening here is our telescope is actually a little bit too big to take really detailed images of planets. So that's because the planets are very, very bright and our telescope is comparatively large. So what's happening is that even at shorter exposure times, we are kind of just blasting our camera with too much light, and we're not able to bring out a lot of fine features. So it's a little bit unfortunate how that works out, but it is what it is.
Actually,
So
it looks great. If you could zoom in on that one more, I mean, you can actually, there's a polar cap on Mars. You can see some dark features. It's yeah, I mean, this is, planets
you're cutting out a lot, Peter.
be a little bit blowy to the Earth's atmosphere, but oh, sorry. Can you hear me now?
Yeah,
Yeah.
I guess not.
I can hear you.
Okay. Yeah, so we can actually see a bit of a polar, yes or no,
Yeah, we can hear you.
William?
I can hear you, yeah.
Okay. Yeah, so there's actually a bit of a polar cap here, and you can see actually some surface features, so it's really nice. Yeah, my internet connection's not being stable. So I'll turn it back over to you, William, and you can move on.
Okay, yeah, thank you. So, yeah, so you can make out a few features here and there. I will say the best view of the planets with our telescope is through the eyepiece by far. So hopefully when the pandemic settles down, you all can come back and actually look through the eyepiece, and you'll be treated to a much better view of the planets than I can show you with the CCD. But on the flip side, with using a CCD, we can actually see a lot of fainter objects in the sky that we wouldn't be able to see otherwise by using the eyepiece. So we're going to go ahead and slew to a different object. We're actually going to go to a galaxy right now. Andrew, could you take us to the Triangulum galaxy?
Yeah, so I was actually having some trouble gaining control of the telescope, so I was wondering if someone could slew that
Oh,
over
sure.
for me.
Sure, yeah,
Sorry
yeah.
about
Yeah, go ahead. Yeah, I'll do that.
So for everyone who don't know exactly what the Triangulum Galaxy is, it's also informally called the Pinwheel Galaxy, and a more technical word, I guess, is Messier 33. And it's a spiral galaxy just like our galaxy. So there's a lot of spiraling arms that extend outwards where stars will form along those long arching structures. Um, and it's actually in our local group of galaxies. So it's the third largest galaxy, with Andromeda being the largest and our Milky Way galaxy being the second largest. But this one's not super small. It's about 60% the size of our galaxy. So it's about 60,000 light years in diameter. Ours is about 100,000 light years in diameter. So those are the sizes we're talking about. And it has about 40 billion stars as opposed to our 400 billion star galaxy. What's interesting is that our galaxy, Andromeda, and the Triangulum galaxy right now are kind of like in a huge cosmic dance where they're held together gravitationally and moving around each other. There's a lot of evidence that suggests that it had a large interaction with Andromeda galaxy about 2 to 8 billion years ago due to some unique star formations involving hydrogen. I don't know quite the details about that, but I know it has to do with the types of stars that it's forming, differences in star formation in one of the arms as opposed to the opposite arms. So that's how astronomers and scientists know that it collided at one time with Andromeda, and it's expected to do that again, either with our galaxy or Andromeda again in about 2.5 billion years. So that'll be pretty interesting for anybody alive in 2.5 billion years to see. And then it's also something called an ultraluminous. It also has something called an ultraluminous X-ray source at the center of its galaxy. So what that means is it's not something that our galaxy has, which has a lot more energetic X-ray source in the center of a galaxy by a supermassive black hole, but it emits more consistent X-ray sources, and we don't really know what that's from. So that's one hot research that's going around right now involving the Triangulum galaxy. Is that the image right there?
Well, in theory, it doesn't
theory.
particularly look very
Doesn't
good
look like
or
a spiral galaxy,
much
but
like anything. Yeah, it's possible we're looking at a patch of clouds. We had a little difficulty imaging another galaxy tonight. Usually we can make them out fairly well, but this one's giving a little bit of difficulty. Do you know what the apparent magnitude of this is, Andrew?
I do not. Let me try again to connect to the telescope.
Yeah, Andrew, I don't think we kept you up to date with the TeamViewer issue that we were having. So we use a VNC viewer now because TeamViewer kind of hates us. So
Okay, I might have to work on that later.
yeah, I can get you up to speed on that.
Okay.
Yeah, sorry, that completely slipped my mind.
Yeah, it's okay. It's all good.
Yeah.
But that's all I have really for the Triangulum Galaxy right now. If anybody has any questions, you can ask in the comments.
Yeah, so sorry I don't have an image up for you right now, but this is just one of the joys of taking real-time data. Sometimes unexpected things happen, like clouds, or it's possible I just didn't take a long enough exposure. So we're going to try for 2 minutes. What I just did was a 1 minute exposure.
That was me messing around with the telescope, so you know, Will.
Okay.
Yeah, part of that is the moon is up.
Oh yeah, that's right.
A pretty bright.
The apparent magnitude, by the way, should be around 5.5, 5.72.
Okay, yeah, we should be able to see this without much difficulty. So, yeah.
I don't know, it's at 10.
All right, so just about 20 more seconds left on this exposure. We can see what that gets us. Okay, so let me just fiddle around. What I'm playing with right here is actually what's called the screen stretch window. It's just mapping the brightness of the light that we're collecting, so the brightness of the photons. And man, I do not see a galaxy in there. Let's see.
I hear well, if you want to describe it.
Yeah, well, yeah, it's possible we're looking through some clouds. So I'm not entirely sure what to.
You know, if we had an all sky camera.
Yeah, so
Inside joke, guys.
yeah, so Andrew, is there anything right quick since we can't get a very good image of Triangulum, is there anything you just want to highlight a second time just so everyone
Well, not about the Triangulum Galaxy. I wasn't sure if I should mention it because we're past it, but it was about the Lagrange point. So I remember someone explaining to me basically the Lagrange point. The way I like to think about it is like if you've ever been on the highway and you have to take an exit and you have to do a really strong turn like around a huge curve and you can really feel the pull, but it's probably illegal. But if you kind of drive towards the inside of the road, you can feel the less of the pulling, the centripetal force. I like to think of it like that. So if you drive kind of closer to the railing as you're turning on the exit of the highway, you can feel the pull less. If you go too far, you'll get pulled out. If you go in, you'll drop in. So it's that perfect point where you don't really feel it, the pull, as you drive around. That makes sense.
Another way that I've heard described is, imagine that you have a wavy surface and you have a marble. And so if you put the marble on any slanted incline or any incline on that surface, that marble is going to move. It's going to basically fall downward. If you put the marble on the top of, say, a peak of that wavy surface, that marble is going to stay where it is, but it's very easy to basically perturb it or knock it. And when you do so, it's going to move. It's going to fall down that peak and fall into a valley. But if you put the marble into the middle of a valley, then you can perturb that ball, and it's not going to move very much. It's basically going to sit where it's at. And so Lagrange points, particularly the Lagrange point that Dr. Rebull was talking about, is more of that pit where essentially that's where it's going to sit. You can perturb it, you can gravitationally kind of tug at it, but it's very resistant to moving. That's kind of how I look at it.
Okay, so thank you for that little side discussion. So let's try our luck with the Andromeda Galaxy here. My VNC viewer got a little wonky. Let's see. So is the dome in motion? Yes, let's see this. All right. So let's just try for a, we can try for a 2-minute exposure. So, and apparently we do have clouds. So that is going to put a little bit of damper, that's going to be a little bit of a damper. But, oh well, that happens. At least we saw a globular cluster and we saw Mars. So we'll try to image Andromeda. Maybe we'll get lucky and see a break in the clouds. But yeah, this kind of thing happens. I know for a lot of the Evening Under the Stars events we've had this semester, it's just had to be completely closed dome. So it's good that we got to see at least a few things tonight. So thank you all for being patient and bearing with us while we try to take some images. So like I said, right now, just taking an exposure of the Andromeda Galaxy.
So William, if I take control for a second, I'd like to describe what you're viewing here.
Oh, sure, yeah,
so
go
you
ahead.
Want to explain what you were showing in this night sky view here?
Yeah, sure, I can talk about that. So one of the great things about modern astronomy is that a lot of our work is computerized. So we have a nice set of software that can control the telescope for us. And what we're looking at here is the interface or the software that we use to steer the telescope and point it at various objects. So this view right here on the right that has a bunch of constellations, this is a live view of our night sky in Fairfax. So this is telling us what objects are currently available. So This orange line represents a horizon line that's about 15 degrees above the horizon. And that's just kind of a software limit that we've set because we don't want to point the telescope too low. You will undoubtedly notice this giant red thing streaking across the view, and we don't really know what that is. As far as we're concerned, it's a glitch or some kind of bug that shouldn't be there. But aside from that, we have, like I said, a realistic, accurate view of the night sky. And if I see something I'm interested in, say this bright star right here, I can literally click on it. It'll tell me the name, Capella, a very bright star, and I can just hit slew. And this yellow dot here that's representing the telescope, it will move across the sky and land on Capella. And it does all of that work for me. I don't need to fiddle with moving the telescope myself. So as long as it's calibrated correctly, it's a very wonderful system to have. So if I pull this up, we do have something that looks like a bright core. So I might be able to one of the noticeable features, if you can get it right, are dust lanes in the Andromeda Galaxy. And I think we can see a couple small ones. I believe those are small dust lanes. I'm not 100.
Yeah, I'll give it a shot, Will. I
Yeah,
got
okay.
connected to the VNC, so I'll give it a shot. Yeah, it's unfortunately the bit depth here with the Chrome Remote Desktop is not really efficient to do it.
I've got something I can try.
It's compressing the image too much.
Yeah.
Okay, go ahead.
All right. Yeah, ordinarily that would do it. So we have clouds, or we won't be able to see dust lanes due to clouds.
Well, that's unfortunate. But yeah, it happens. But we do see a very, very bright core. You can see how that is outshining a lot of the stars in this field of view. So that's just because there's a supermassive black hole at the center of this galaxy that's accreting material. So one of the most remarkable discoveries in recent astronomy is that most massive galaxies have a supermassive black hole at their center. And a lot of the time, that black hole has an accretion disk around it. So there's a bunch of gas and dust that's orbiting around that black hole, and it gets very heated. And sometimes you can get jets of material that are kicked out of the galaxy, and you get these really, really powerful winds and other phenomena. So it's unfortunate that you can't really see it here. The only thing you can really see evidence of is this very, very bright nucleus that's going to be powered by accretion. So if I dim this a whole lot, you can see how bright that is in relation to all of the other stuff that's very, washed out and dim at this level of contrast, and we just have this incredibly bright central nucleus here, and that is the Andromeda Galaxy. So I know it's not very impressive. The clouds really are kind of not being friendly to us tonight, but
I've put into chat an image that I took using this telescope of the Andromeda Galaxy to give you an idea of what you would be able to see in good conditions. Hopefully you guys can access that.
All right, thank you, Rob. So that's does anyone have Andrew, Owen, Ashley, anything you want to say about the Andromeda Galaxy?
I could add something to it. If you could go out and in a dark countryside and a clear night, you can actually resolve Andromeda with your own eye, just the bulge part. It may appear like a faint, fuzzy blob. And the disk itself is so faint, you might not be able to resolve it. But if you were to include the disk, if you were able to resolve the disk, the width would be about 3 moons across. So that's how big the Andromeda Galaxy would look like up in the night sky. And of course, over the next couple of million years, it's going to get a lot bigger.
Yeah, wonderful. Thank you, Justin. So we don't particularly have any other objects in mind for
Well,
tonight.
Will, let's take it home to the moon and call it a night, and let's
Okay.
wrap up on the moon.
Okay, yeah. Is the moon gonna be available?
Oh, it's a little low, isn't it? Let's go to it anyway. It's a little low. It's towards the east, but we can go to it since it's so bright.
Really now. Let me just see.
It's there.
Yeah, so we're in a little bit of an awkward spot in terms of things that are available in the night sky. The Orion Nebula isn't quite up yet. The Eagle Nebula has just set. So that's two interesting objects that aren't quite available at this time. So you just got to make do with what you have. And are you sure this thing's not going to smack into the ground? Oh, no, it's not. Okay.
Yeah, I'm sure. It just stopped.
Okay, yeah. Okay, cool. So, bar any absolutely major clouds, we should be able to get a fairly nice view of the moon. Oh, I bet I didn't wait for the dome to catch up, did I? Yeah, the dome is still moving, so we're not going to see anything with that exposure. Okay, so let me take another one. Let's see here.
Looks like we got clouds, unfortunately.
Yeah, we could be looking at clouds.
Wow,
That
that's
looks like cloud cover.
yeah, that is a bummer.
You may also want to try H alpha
Okay.
as the filter, William.
Yeah, I can try that. Oh, little peek of the moon there.
Yeah, it's just you got it though. There it is.
Yeah, we can definitely get a lot better views. We're definitely looking at a bunch of through a bunch of clouds right now. But you can see some of the cratering features that are on the moon. So let me go and try with H alpha next. But you can definitely make out a few craters on the moon and some brighter patches. And if the clouds would go away, we would get a really wonderful view of the moon. Being low on the horizon doesn't help either, because you're just naturally looking through a bunch of air. Oh boy, let's see here. Oh, there we go. That's definitely a lot better. So now we can see a lot more details. We have a bunch of craters, some ridges, and a lot more features that we can very easily see and make out. So unfortunately, I don't know the names of the craters and surface features on the moon incredibly well, so I can't exactly give a good guided tour around the moon. But one thing, One thing that's important, or I guess good to note, is you can probably notice that towards the middle of the image where there's more shadow, you can see a lot more detail, and that's actually a good way, through the best way to view the moon when you look along what's called the terminator, the divide between the light and the dark. So it's that contrast that's going to bring out a lot of the details. So if you're looking at this with your own smaller telescope, you don't want to point it, directly, at the brightest part of the moon. You want to point it along the terminator.
Hey, William, I can talk a little bit about the moon.
Oh, sure. Yeah, go ahead, Ashley.
All right. So, yeah, the moon is the closest astronomical object to us in the entire universe. So it's kind of cool to think about that. You think of all the things we've looked at tonight. The moon is literally the closest astronomical object that can get to us, or that we can get to. So that's pretty unique in that respect. And it is also not, we call it the moon, but there are actually a lot of moons in the solar system, like Saturn has moons, Jupiter has moons, and our moon is actually not even the largest moon in the solar system. It's actually the 5th largest moon in the solar system, and number 1 goes to Ganymede, which goes around Jupiter. But yeah, it's only a quarter the size of the Earth, and it's about 380,000 kilometers from Earth. And as far as those features go that you guys are seeing, the dark gray spots are actually called Maria, kind of Latin for sea. They're just smoother areas on the moon's surface. And then the highland crater areas are called lunar highlands, and they're more heavily cratered and whatnot. And so a cool little thing about the moon is that it is always facing us. This image of this side of the moon is always facing us. You guys don't actually see the other side of the moon ever, because the moon's kind of in a geosynchronous orbit, so it always orbits the planet facing the same way. But we have sent satellites and probes to look at the other side of the moon, and it is actually all crater. There's not all this Maria that you see with the gray and the dark gray spots that you see all over the front there. But yeah, that's an awesome image of the moon, and you can actually see the that really large swath of gray. That's the biggest Maria area of the moon that we have, and then again, all the little smaller craters are the highlands. So yeah, that's what I have on the moon.
Yes, some of you may have just heard that the moon was just in the news. I believe it was this Monday or a week ago this Monday. NASA has a release finding water on the surface of the moon. Now, we've known the moon has had water at its poles in the form of ice frozen in the craters that are constantly in the dark 24 hours a day. Well, the moon doesn't have days per se, the day lasts a month. But this latest discovery was a bit of a surprise. At a place away from the poles of the moon, there was actually water on in the mare, but it's 100 times drier than the Sahara is on the Earth. So very, very little. You have to get a lot of soil just to squeeze out a few ounces of water. It's in such tiny amounts, as Owen said. But there was a great question that we do think that there is some a sufficient amount of trace amounts of water on the moon that could theoretically be usable in a future lunar colony. Back to you, and Will.
Okay, wonderful. Thank you, Peter. So I think it's about 10 o'clock now. We've gone on for about 2 hours. So unless there are any additional questions, I think this would be a good ending note. So thank you all for coming out tonight. We hope you enjoyed the talk. If there are any additional questions, please feel free to ask them. But otherwise, thank you all. Hope you enjoyed it, and I hope you all have a good night.
Yeah, have a great night. This talk will be posted to YouTube on our website. And thank you all for coming to our evening under the stars. The humidity held off, and it was great. The clouds didn't, but it was great to give you some views of the night sky tonight.
Thank you. It was a pleasure.
Thank you. Glad you liked it. .32-inch diameter aperture, Charlie.